Welcome to the Plant Floor Air Proofing Seminar. This seminar is designed to discuss options for implementing process control within manufacturing. So, why are we discussing plant floor air proofing? One main reason is we know your company's focused on transitioning into Industry 4.0, and the use of plant floor air proofing devices are what's going to help you get there. All right, Industry 4.0, I'm sure you've heard of it by now, and we'll discuss what Industry 4.0 actually means, but each progression you see here is considered a new industrial revolution. The first industrial revolution was the use of steam engines within manufacturing, which was a big deal because it allowed manufacturing to be operational in areas that weren't close to water. The use of man, water, or wind power were no longer requirements as they could use a steam engine to drive reliable power used for heavy machinery. The second industrial revolution is the use of the assembly line within manufacturing, which is what enabled mass production. Henry Ford is most commonly referred to with Industry 2.0 because Henry Ford is who made the assembly line popular. The third industrial revolution is really the true beginning of automation in airproofing itself and is where the use of computers and semiconductors made processes more repeatable and safer. All right, we finally made it to Industry 4.0, but what is it? You may refer to I 4.0 as big data or Internet of Things, but Industry 4.0 is the use of data from interconnected devices in order to make decisions in real time based on what's happening within a manufacturing environment. It's no secret quality is a major focus area within your production environment, and that's because building bad products will impact the company in multiple ways. This standard hasn't changed since the beginning of any type of craftsmanship. Quality will always be very important. A subpar quality product can affect brand perception, having a compounding effect. An user may lose their brand loyalty if they don't trust their products for use anymore. And notice how I said products here as in plural. That decision could carry over into other product lines your company's building. You may also want to consider how losing these customers realizes a market share loss and a direct financial impact. This is a real possibility if your competition's building a better quality product. So, whether we like it or not, humans influence build quality. When comparing an experienced operator to one who's new, quality improvement is usually evident, and at the same time, a byproduct of experience is efficiency. With that being so, think about it like this. Even a highly trained operator with a ton of experience can and will make mistakes. Some of those mistakes may be forgetting where they are within the build process, which could result in multiple missteps, using the wrong tools and or programs for the job, which could result into a product built outside of its design specifications, using the wrong parts for that specific build, repeating the same work sometimes more than twice, and performing the work in the wrong order. So as this world turns, it's getting more and more automated, and hearing just about some of these mistakes humans can make, you're probably asking yourself, why should we use people to do this work? Think about it like this. Most of your manufacturing environments are dynamic. They're changing daily, maybe even hourly. And to simply put it, they must be fluid to design changes, product improvements, supplier changes, and or process changes to create efficiencies within production. When we look at humans versus robots, humans have a clear advantage as being much more adaptable. A human can relearn a process rather easily. When we look at robots versus humans, the advantage for robotics is they're very repeatable as they're able to do the same process over and over again with very minimal deviations. So we know how dynamic our manufacturing environments are. Now do you see the advantage of using humans? A robot may need physical changes to the equipment it's using when product designs change, and it'll certainly need programming to perform these new tasks. The programming is usually not limited to the robot itself either, because you'll likely need to program the equipment it's using for the new task. The robot might also need to be physically moved when changing the manufacturing process, and as you can imagine, this usually doesn't happen overnight. I think we decided let's use humans in manufacturing, but we still need some things in place to make sure we're reducing or eliminating as many human errors as possible. We can do this by using hardware and or software specific for controlling different areas within manufacturing. If you're familiar with the 5 layers for automation, the schematic might look familiar. For the purpose of this presentation, I've reorganized and renamed some of these layers to focus on which assignments in manufacturing we're looking to control. At the lowest layer, the core layer for eliminating human errors, you'll see the operation layer. This is where we're able to control the work performed by the operator on a specific task at one time. The next layer up is called the process layer, which we're looking to control the work performed within a specified sequence of tasks. Now let's look at the progress layer, which is where we're looking to control the work performed throughout the entire build specification, and this includes the validation of the build performance. This layer is most often handling rework scenarios when errors do occur. At the business layer, we're only looking to control what we're building and validating we have the right supplies to do so. Finally, at the adaptive layer, we are looking to control and make decisions by evaluating data received at all layers based on trends or any deviations in real time. All right, let's start at the lowest layer, the operation layer. This is where we're using measurement equipment and devices to qualify our tasks are being met accurately and to within our specifications. In this layer, you'll use devices such as smart tools, torque controllers, actuators, smart cameras, and sensors. These devices are not usually limited to measurements, but also likely provide an evaluation of the task being performed by simplifying what has happened. A common way to do this is to give feedback with an okay or not okay for the status of that task. The operation layer is the base to becoming a zero-defect manufacturing environment. These devices are what enable error proofing and essentially are closest to the operator. So, what are the pros and cons when evaluating using measurement equipment alone as a control mechanism for error proofing? The pros are these devices provide assurance to a specialized task as to being complete and to within their specifications. They're usually managed by the manufacturing engineers or quality engineers who have the most knowledge on how to build to their design specification. But the cons are when programming these devices, this usually requires a specialized skill as they're likely programmed or configured in some sort of proprietary method. These devices are usually limited to measuring one task at a time. Some of these devices don't usually have a way to communicate to higher level systems. In the process layer, you'll find devices like PLCs and SCADA systems. These devices are most often responsible for implementing control within a station. They are used to ensure specific sequences are being met and have been around since the late 1960s. The pros of using PLCs and SCADA systems to enable process control are the pros being they provide assurance to a sequence of tasks as to being complete, and they're generally easy to program and set up, but the cons are they lack a focus on the human experience. The setup is rigid because it's based on interfacing the physical devices. There's usually multiple layers of programming to consider, being the PLC itself, but also the measurement equipment it's speaking to. And they're managed by the controls engineers, who usually are not the experts in manufacturing. At the progress layer, we're looking to control, validate, and manage work and rework for the entire product's build specification. The device doing this is what's called a MES, Manufacturing Execution System. The MES is a software-based system monitoring all work in progress, and it specifies or audits sequencing of a product build to validate the product is being built in the correct way. So what are the pros and cons of using MES to implement control within manufacturing? The pros are the MES is a plant-wide solution, has access to all devices in some way and all layers. The MES is usually most capable solution for error-proofing and embedding control. It's designed to integrate with existing devices within manufacturing environments like PLCs, SCADA systems, and ERP systems, which allows them to enhance already running plants. The cons are the MES is not very agile, and changes within MES are usually complex and very slow to implement. When changes do occur, the risk is very high. The MES usually doesn't focus on the human experience, and the MES is controlled and managed by IT departments, who themselves are quite removed from the needs of manufacturing. In the business layer, you'll find the ERP system, which stands for Enterprise Resource Planning. This software usually connects and manages supply chain inventory and ordering, business and plant financials, human resources, but enables lean manufacturing by communicating to the MES to build what product and model that is being ordered within a specified time. The ERP system usually has the least amount of control within manufacturing, but does play a crucial role. Pros and cons of the ERP system is the ERP knows what people buy and it does enable lean manufacturing, but the cons are controls limited to communicating only with the MES as to what to build. It's managed and controlled by IT and financial departments. This may be a pro depending on how you look at it, since the ERP system's not designed for controlling the entire manufacturing environment. All right, the adaptive layer. This is where we're going to make better decisions in real time within manufacturing. The system will have access in some way to all devices and layers we just talked about. The adaptive layer is a core component of Industry 4.0, as it'll be able to detect anomalies within manufacturing and force action to reduce downtime, optimize operational time, and reduce the product's time to build and or test. It's safe to say that not many manufacturers are using the adaptive layer yet, likely less than 5%. And it's also safe to say that whoever implements this first and in the correct way will have and create a competitive advantage. Pros and cons of using AI in your plant are the pros being has access to all layers within manufacturing and will make decisions based on what's being seen in these layers. It's designed to improve uptime, quality, and reduce time to build. The cons are it needs massive amounts of data and the correct data models to make good decisions. It will not offer full control within manufacturing and really shouldn't be dedicated for full control either. And usually AI is going to be owned by third parties. So let's look at the timeline of airproofing within manufacturing. In 1961 was when Poka-yoke was introduced and this began to be widely adopted. Its meaning is to avoid careless mistakes. Many use this model to implement processes within manufacturing and begin the concept of airproofing. In 1960, relay logic control panels were born. These devices are really the beginning of external devices implementing some forms of control, and they were mainly dedicated closed-loop systems with drum sequencers, cam timers, and thousands of hardwired relays. They were built specific to a singular application, very expensive, and not modular at all. In 1968 was the birth of the first PLC, which came from a request by a GM. The request was to develop a new system that would be flexible like a computer, easy to program using ladder logic, had interfaces that were replaceable. The PLC was a mix of hardware and software. In 1990 is when MES and ERP systems were born. These systems were designed to fill gaps left behind by the PLC regarding planning and build validation. Both MES and ERP systems are software. In the year 2000s, when machine learning was introduced, AI is built to reveal any slight deviations using trained data models. Machine learning is built on software. Do you notice a trend? I'm sure you guessed it, but that trend is since 1990, all the advancements in control and airproofing have been from software. But why is that? Software is agile, it's adaptable, and business models need to be dynamic and changed often. The market's changing often, and your demographics might be changing often as well. It's critical that your manufacturing environments are able to change at the same rate. Industry 4.0 is about making changes in real time by being well informed through data analysis. The core component of Industry 4.0 is software. So we've identified there are multiple ways to reduce human errors through process control, but is there a perfect solution? And if we were to reply yes here, what would that model look like for that solution? The perfect solution should focus on the human side of things, making the person's jobs, experiences, and lives better. How can we do this exactly? Well, we can do this with a better interaction to the operator by guiding them through their processes using a simplified interface. It should be flexible to the ever-changing manufacturing environment. Changes should be made easily with little risk to the operation. The solution should give power back to the manufacturing engineers, the experts in manufacturing who are focused on building the specification with the highest quality possible. It should allow for scalability, giving you the options of enabling more control where it's needed, like safety and quality critical applications, and leaving out unnecessary steps where it doesn't make sense. This enables your manufacturing environments to be lean while focusing on quality and throughput at the same time. It should be an intelligent system that can connect to many different device types easily. It should be able to integrate to your current architecture, which would be crucial. How many of you would consider a total redesign of what you're using today? Now, how many of you would consider an adaptation of your current architecture? Sure, a lot more. Collect and report data from all devices connected. So we've been talking about enhancing the user experience through this presentation, but what exactly do we mean by this? We want to make operators' lives easier, and we can do this a few different ways: by walking the operators through their workflow on screen in a linear progression, by focusing on how the operator interacts with the equipment they're using within the operation, like enabling, disabling tools, present the tools with tool ready lights, automatically change programs for each bolt sequence in every model variant you're building. Also, like tracking all workflow steps with all connected devices by capturing values, status, and acknowledgments for data analysis and other administration functions. Making sure the operator is trained to work at the station with access control and user identification. Making sure the product is in station, that we're doing the correct build for each unique models, and validating parts are correct before we even run. But the human experience doesn't just end with the operator. We talked a lot about who's managing these control systems throughout your plants. The goal is to change ownership to the team with the job function of production quality, who is the manufacturing engineers. This would allow for agility and minimize risks when making any process changes. So how do we do that? Well, we can do this with how we manage the configuration of the process control software. For example, the configuration utility should allow a manufacturing engineer the ability to easily program what the operator sees and how it's running the equipment. So we showed how important data capture is and its relevance to Industry 4.0. Your enhanced plant floor airproofing system should capture data relevant to the plant floor across all devices connected in real time. Okay, so what are the benefits of using software to replace or coexist with your current process control architecture? Well, this software should give power back to the manufacturing engineers. It should emphasize control at the progress and process layers. It should be able to have access to all controls where it's needed, provide assurance that all tasks are being complete, scalable from a station to a line to a plant or even a company-wide solution, easy to set up and program for agility within the manufacturing world, focus on the human experience to make operators and people who are configuring the process control devices' lives better, and is low risk when you implement any type of changes. All right, so our whole goal here is to increase quality and repeatability while keeping you as flexible as possible to the many necessary changes within your plant, while keeping a focus on the operator for a better overall experience. And by using software, we can do this in a lean way. Thanks for your time. I hope you found today's seminar educational. If you have any questions, please contact your local Atlas Copco representative for further details.